Okay. So we'll continue. We'll continue with minus. So minus you will represent as Mij. So minus is nothing but, a minor is nothing but a determinant corresponding to the element in the matrix. Correct, Amma? Next,
Yes.
you have cofactors. So cofactors are nothing but Cij. Cij is given as Cij is equals to minus 1 to the power of I plus j into Mij. Right? So for even, it will be positive. For odd, it will be negative. Then you have adjoint. Adjoint is nothing but Cij whole transpose. Right? Correct?
Yes, sir.
Right. Next. We have some properties, Nana, properties for adjoint. And these are important. And especially this one is very, very important. Adjoint of A is equals to determinant of A into In. That is equals to adjoint of A into A. Next, determinant of adjoint of A is equals to determinant of A power n minus 1. Determinant of adjoint of A is equals to determinant of A power n minus 1 whole square. Then adjoint of A is equals to determinant of, determinant power n minus 2 into A. Adjoint A whole transpose is equals to adjoint of A transpose. Adjoint of AB is equals to adjoint of B into adjoint of A. Adjoint of A inverse is equals to adjoint of A power, adjoint of A whole inverse. Also, you can say adjoint of A power M is equals to adjoint of A power M. Okay. Clear? This is important. You are going to get problem on maximum on this adjoint thing. Clear? Can I move to the next one?
Yes, sir.
Next, inverse of a matrix. See, let us say there is a matrix A of order M by M. Then there will exist a matrix B of order M by M such that AB is equals to BA is equals to I. Or simply I can say B is equals to A inverse or A is equals to B inverse. Here this A inverse is nothing but 1 by determinant of A into adjoint of A. But the condition is the determinant of A must not be equal to 0. So it should be a non-singular matrix. If determinant of A is equals to 0, then inverse does not exist, sir. If determinant of A is equals to 0, you will call it a singular matrix. Okay? Clear?
Yes, sir.
Next. Once again, there are properties, sir. Properties for inverse. So A transpose whole inverse is equals to A inverse whole transpose. AB whole inverse is equals to B inverse into A inverse. A inverse whole inverse is equals to A. K into A whole inverse is equals to 1 by K into A inverse. K not equals to 0. AB equals to AC. That would imply B is equals to C or BA is equals to CA. If BA is equals to CA, that will again imply B is equals to C. Okay. And if determinant of A is not equals to 0, then A, and if A is symmetric, that would imply A inverse is also symmetric. Okay. And see, there are basic elementary operations. How many operations are there? Number one, interchanging of any two rows or columns. You can simply say R1 is interchanged with R2 or C1 is interchanged with C2. This is one condition, sir, interchanging. Number two, you have multiplication of rows or columns by a non-zero number. So for example, let us say there is R1. So you can rewrite it as KR1, where K is not equals to 0. And you also have multiplication of row or column by a non-zero number. This is not part of your CBSE, sir. That is why I am discussing. The multiplication of row or column by a non-zero number and add result to other row or column. So for example, take R1. So R1 can be written as R1 plus or minus KR2. We can write plus or you can write minus. So that is another possible thing, sir. Okay. Next. There is something called submatrix, sir. Submatrix of A. So submatrix is nothing but matrix obtained by deleting some rows and columns of a matrix A. And as I told already, singular matrix means determinant of A is 0 and non-singular matrix determinant of A will not be equal to 0. And here one important point, if A is singular, then adjoint of A is also singular, sir. Okay. Next. There is something called characteristic equation. determinant of A minus lambda I is equals to 0. This is called characteristic equation of A. And every matrix which satisfies this condition, you will find that using Cayley-Hamilton theorem. Okay. And there are certain properties for determinants, sir. Number one, determinant transpose will be equal to determinant only. A det or a determinant with all zeros in a row or column, then the determinant value will be equal to 0. A determinant is equals to 0 if any two rows, determinant value will be equal to 0 if any two rows or columns are identical. If they are same, then determinant value will be equal to 0. If any two rows or columns are interchanged, then the determinant formed will be minus value of that determinant, negative value of the determinant. Then next, determinant transpose, that is D dash. Let us say it is KA1, KA2, KA3, B1, B2, B3, C1, C2, C3. So if you observe this type of a determinant, it will be equal to K times the determinant value. Okay. And I will give you some standard results, sir. So for example, you see something like this: 1, 1, 1, A, B, C, A square, B square, C square. If you observe increasing in rows, 1A, A square, 1B, B square, 1C, C square, then the result will be A minus B into B minus C into C minus A. The same thing you reverse: 1, 1, 1, A, B, C, A square, B square, C square. Then the value will be A minus B into B minus C into C minus C A into A plus B plus C. So this part is extra added. And if you have determinant like this: 1, 1, 1, A square, B square, C square, A cube, B cube, C cube. Then A minus B into B minus C into C minus A is common, sir. Instead of A plus B plus C, you will have AB plus BC plus CA. One more important one. If the matrix is a cyclic, if the determinant inside is cyclic, see ABC, BCA, CAB. If it is cyclic, then it is minus of A cube plus B cube plus C cube minus 3ABC. Please remember, important observations. Okay, clear?
Yes, sir.
Next, let us say they give you one triangle and ask you to find the area of the triangle using determinants. Let us say this is A x1 y1. This is B x2 y2. This is C x3 y3. So what would be the area of the triangle? So area of a triangle is given by determinant of half of determinant of x1 y1 min. This is modulus, sir, not determinant. Modulus of determinant of half of x1 y1 1, x2 y2 1, x3 y3 1. If determinant is equals to 0, you already know the points are collinear. Am I right, sir?
Yes, sir.
Next. Next, I will talk about homogeneous equations. Let us say AX is equals to 0. Now two conditions are possible. Determinant of A is not equals to 0. Determinant of A is equals to 0. If determinant of A is not equals to 0, sir, then you will have trivial solutions, sir. That means X value will be equal to Y value will be equal to Z value will be equal to 0. If determinant of A is equals to 0, then you will have infinite solutions, sir. Trivial and non-trivial. And always remember, sir, homogeneous system, it is always homogeneous system, it is always consistent. Zero comma 0 comma 0, this is called a trivial solution. And homogeneous system has non-trivial solution also. Non-trivial also if determinant of A is equals to 0. That is what I have represented in one small diagram, sir. That's all. Next, Cramer's rule. Again, two cases. Determinant is not equals to 0. Determinant is equals to 0. Again, in these two cases, if D1 equals to D2 equals to D3 equals to 0, then it is consistent and it has a trivial solution. If D is not equals to 0, at least one, that is D1 comma D2 comma D3 is not equals to 0. If it is not equals to 0, if at least one is not equals to 0, this is consistent, but it will have unique non-zero trivial solution. Again, coming to this case, D equals to 0. If D1 equals to D2 equals to D3 equals to 0, it is consistent. It will have infinite solutions except parallel lines. No solution. One of D1, D2, D3 is not equals to 0. Then it will have inconsistent solutions. Clear?
Yes, sir.
That is about matrices, sir. And tomorrow if you join, I'll talk about vectors.